postdoc at MIT, then went to a faculty position at McGill University, and then went back to Technion, where he's a professor. Today he's going to talk about robust PCA.
So I don't know where should I stand given the intercontinental setup. So, all right, let's stand here. So today I'm going to talk about robust PCA for high-dimensional data, and that's joint work with Huan Chu and Constantine Karamanis. And that's a paper that appeared and called this year. And I think it's kind of interesting. I thought it would be interesting for you guys. It talks about what to do when you want to do PCA and you have contaminated data. And as we know, PCA is extremely sensitive to contaminated data. So even a single bad apple can open the whole viral. I'll talk about it in the context of PCA, but really what's lurking here is a much more general problem, and there are two problems that this talk is a special case of. So the first problem is what we call data-driven stochastic optimization. So you want to optimize a function, a stochastic in the expectation of some omega that distributed in a way that you don't know, and you have samples of this problem, but a constant fraction of the samples are corrupted, and maybe even chosen by an adversary. That's a problem that is I'll motivate it from excusing with the non-Google perspective, but even an can be chosen by an adversary that knows your algorithm. Now the other problem, which is more machine learning-like, is finding hidden structures. So you have a noisy measurement, and you have some structure there, and there are many examples like manifold learning and compressed sensing, and basically we want to find hidden structures. So this talk is about a very simple case, which is a case of PCA. So here, the function that we try to optimize is sort of variance, so the x transpose omega, and the hidden structure that we look for is a low-dimensional linear manifold. So this is sort of, if you want to solve those two problems, that's probably where you should start. So you should start with something that's low-dimensional linear, and the function here is more or less, the random function. That's as simple as it gets. And that's really what this talk is about, and we'll focus on PCA because it's tractable and relatively easy. But the goal is to try and solve those data-driven stochastic optimization problems that are important throughout engineering, and to figure out how and if we can find the hidden structure when we have contaminated data. So let's just, I'm not sure if everybody here remembers exactly what is PCA, so probably the answer is yes, but just sort of let me recall the details. So we observe high-dimensional points and want to find the best approximation, which is a least squares approximation. And this is done in essentially every field of engineering. And machine learning people are not the one that use it most, surprisingly. But image processing and data analysis are done extensively, but also in communications and networks. So there are many applications where you do feature extraction and when you do compression. So this is just a picture to fix ideas. So here we have a signal. The signal is sort of this line here. And we have some noise, and we assume that y equals ax plus v. So a is a matrix or our signal. X is the data that we multiply by a, and we add some noise, and you can assume whatever you like about the noise for now. So we have a signal, and it's perturbed a little bit by small noise, and you see, this is the picture that you're going to see. Everybody's happy. You can learn it. And you can find A, and that's going to be the least square error subspace approximation. So you're finding the subspace that has the minimum error, or equivalently the best compression scheme for your data. So that's PCA. And just a few notes. So what we really do is we do SVD here, and on sample covariance matrix. And that's going to be important to remember. I also remind you that SVD is not a context problem. So we're solving a non-context problem, and using the fact that we're using least square error is crucial here. So everything would break down if instead of least square error you would have something which is a little bit nicer. So if instead you would have something like that tails down in a more comfortable way at the end, for high values, things would break down.
So Shie, Collins, does group and Shapiro have a generalization?
Yeah.
And it's not convex, the result is a greedy approach? Or?
So the result is sort of a greedy approach, to the best of my collection. And basically, the setup of low dimensions is not too interesting for us. So we'll move shortly to the setup where the dimensionality is the same as the number of samples, essentially.
I see.
Okay, and then things are going to break down. So this is a very well-known result that even one outlier can make the output arbitrarily skewed. So I imagine that the example before, if you have one sample here, then that would change everything completely. If you'd had it somewhere over the moon, then your least square subspace approximation is going to basically be destroyed completely. So that's one consequence. And the question you can ask yourself is, what can you do when you have a constant fraction of outliers? And that's one of the topic of this talk. So this is what we're looking into. We're looking into two things. We look at the high dimensional regime. So the number of observations is essentially the same as the dimensionality. But you can always embed the dimensionality to be equal to the number of observations. So this is a regime of interest. This is what we call high dimensional. And there is a constant fraction of points that are arbitrarily corrupted. So your points most of the points come from a model, but some points, and this fraction can be significant, is corrupted possibly by an adversary. Okay. So what I'm going to do now, I'm going to do, this is the outline of the talk, I'm going to start with some motivation, and then I sort of will explain where things get tricky in high dimensions, and essentially the tools, the usual tools are going to fail, and if you want to suggest new tools, I'll try to convince you that they fail too, or rewrite the paper, or write a new paper. And then I'll present an algorithm that we call the HR-PCA, high dimensional robust PCA, and sort of explain a little bit how the proof works, and that's about it. So, high-dimensional data, I don't think I need to convince you guys that high-dimensional data is important. What I do want to mention here is an application which is kind of interesting, and that's application in networks and user-aware network algorithms. So, one of the problems that I've been looking at, as Yoram said before, I'm really an engineer. This pretends to be. Often you have, we are able to collect a humongous amount of network data. So we sample the network, think about an IP network in many places, and we have a huge stream of data, and we want to sort of figure out what's really happening in the network. And it's not very useful for us to just take this data and crunch it and say things like, this node is. We want to understand the way the flow works. So you can run flow equations, and you can get lots of data, and basically you want to figure out what happens in terms of the low dimensionality structure of a network. And that's an application which is pretty cool. And there you get linearity by essentially by Kirchhoff laws. And another reason why high-dimensional data is important is the kernel trick that, of course, generates high-dimensional data. So what we'll see here is that traditional tools do not seem to scale up in this setting. So let me sort of give you an example. So here I have a figure where we have no outliers, and here we do have outliers. Now we think about it in the lower dimensional regime. So, this is a really easy problem, right? Because here are some things you can do. You can just, discard those samples that have large magnitude, or that they have large Mahalanobis distance. Or you can look at the ellipsoid that covers most of the data, and then expand it little by little. And once once you see that if you expand it by little, you don't gain much, but then when you expand by much, you do gain much. It's basically you can cover this set, or this set in this case, and discard everything else. So if you look at what's known as the minimum volume ellipsoid, or the leaflet that contains, say, 90% of your data, then you will be able to discard outliers easily. So in low dimensions, the problem seems to be manageable, and there are lots of good solutions, and they'll all work, and outliers are not really a problem. But in high dimension, none of this is going to work, as I'll shortly convince you. So outliers do not need to have large magnitudes; they can have small distance, and in fact, the volume of the smallest container ellipsoid is 0. So you're not going to change anything there. So our goal is to gain robustness to arbitrary corrupt data, and I'll show them all shortly. One measure to think about is what's known as a breakdown point. So a breakdown point is a concept in robust statistics. And think about the case where you have an estimator, and you're asking, suppose somebody is going to corrupt some samples. So how many samples does this evil adversary has to corrupt so that he can arbitrarily change my estimator? So, for example, in the case of mean, so if there is if you have a single dimensional random variable and you want to estimate the mean, and you take the empirical mean, then if the adversary wants to change it to an arbitrary value, you can just take one sample and put it somewhere, and that's going to change the mean to the adversary will. So he can basically do whatever he wants. If instead we're going to take the median, then the breakdown point is half of the point. So to change the median to an arbitrary point, the adversary needs to change half of the samples. So the breakdown point is a sort of an acceptable measure in robust statistics to robustness. And what we're going to try and look at is that we're going to try and bound the error between the true PCs and the PC that our algorithm is going to recover. And the bound is going to depend on two things: the fraction of the outliers, so how many outliers the adversary changed, and the properties of the distribution of the signal. And that's sort of, if you like, this is really what we're going to do here. So let me just be more precise here in terms of problem setup. So we assume that we have T authentic samples, and the samples reside in some RM, and they have this generative model, so that every sample is a function of signal plus noise. So A is a matrix representing. Basically, we want to find A, and X is some random variable. The noise is assumed to be normal or Gaussian for the sake of this talk, but this is not really important. And A is some matrix which is unknown, and the signal is just zero mean with some covariance. It's not really important what the covariance is. You can change the covariance and push it into A, so we can assume without loss of generality that it's identity. So we have T samples, and those are the authentic samples. And then we have n minus T outliers, and those outliers are generated arbitrarily. So they can be problems in the data set. They can be things that some adversary pushed them as, like in the network problem. They can be just errors. We don't know where they're coming from, but they're generated arbitrarily. So we have n samples overall. T of them are authentic, and n minus T are not authentic. We observe all the samples. And so we observe our observation is a total of n samples, and of course we don't know which is which. So we don't know which sample is authentic and which sample is arbitrary. Now the regime that we're going to work on is a regime that the dimensionality of the problem, that's n. So everything here resides in Rm. And the number of samples is more or less the same and much larger than the dimension of the signal. Or if you like, the dimension of the matrix A, which is what we would like to solve. And what's known as a signal, so in the signal S, which is the size of the matrix A, is assumed to increase to scale slowly with the points or the dimensions. And our objective is to retrieve A. So this is the setup of interest in a more precise way. And of course, retrieving A is impossible, so we're going to settle for something which is like retrieve something that looks like A. And now I'll shortly discuss what the meaning of sigma scales slowly. Okay, so let's try to figure out where things get tricky here. Just before that, I have a question about the setup, because this is a really important point. If you miss that, then you might as well zone out for the rest of the talk. So the setup is very simple. So there is a generative model that generates T samples. The other samples are generated somehow, and we want to retrieve the signal A. So where things get tricky. So the first thing that gets tricky is the noise explosion. So in high dimension, the noise magnitude scales faster. So the noise magnitude scales linearly with the dimension. In particular, the SNR, the signal-to-noise ratio, goes to 0. And this is the first really annoying things about the setup. So just to explain how it goes to 0, if you have an n-dimensional random variable, say Gaussian, then if you look at the norm, the 2 norm, then the 2 norm essentially equals the square root of the dimensionality with very sharp concentration. So this is a result due to Talgrand, and I mean there are many. I mean the concentration is very sharp. On the other hand, the signal. So if you look at the norm of AX, then it's something like the sigma. Sigma is, just to remind you, sigma is the norm of A transpose A times square root of the dimension. So this scales with m. This in square root. This scales much slower. So what it means is that the samples may have much bigger magnitude than the outliers. I mean, the outliers are not big anymore. And it also means that the noise is going to drown the signal. So the direction of each sample is going to be approximately orthogonal to the direction of the signal. And all the samples are going to be approximately orthogonal to each other. So let me just convince you, this is the image that we had before. So, you know, this was our signal, and this was a low-dimensional regime. In high dimensions, the noise is very large. So the signal is really that small, and the noise is large. So the noise is much larger than the signal. And moreover, even if you have two samples that are close in the signal space, once you add the noise, then they can be very far away from each other. So now, to make things even more annoying, every point is more or less equidistant from the origin and from all other points, because all the points reside on a ball in a very high dimensional space. And now now you can start playing with high dimensional probabilistic geometry. So all the points are the same distance from each other and from the origin, and they're all orthogonal to each other. So they're perpendicular to the signal space and are more or less orthogonal to each other. So that's what happens once you look at the regime of the high dimensional regime. And I think that's a regime that's a logical way to increase dimension. So you have noise that is added in all dimensions. Okay. So let's see what we can do. So let's try to come up with some natural approaches. So we can do a leave one out, or more generally a subsample, and then basically we subsample the data, we do PCA, we do another subsample, we do PCA, we compare what we get. Then once we have a few corrupted points in every subsample, then who knows what's going to happen. So once you do PCA and you have a few corrupt points, things are going to end up badly for you. If you have really small samples, then you might not have enough data. So at least subsampling approach may not seem to work. And then you can say, well, let's do the standard thing. So let's do a robust PCA. And in robust PCA, basically we take the covariance matrix and we robustify it. So we solve the PCA problem, but with respect to the worst case covariance matrix, which is close to the true covariance matrix. But this is also not really a good idea because, well, if you look at the covariance matrix, it's going to be a huge matrix in high dimensions. So it's going to be an n square or an m square matrix, and basically you're not going to have enough observations to do anything useful, just because the matrix is so large. So standard robust PCA do not seem to be, it's probably not going to work. It's essentially going to get the covariance of the noise. So now you can say, well, let's remove points with very high magnitude. So let's just throw away bad point. But as I said before, the noise drowns the signal. So we're just going to throw away some points. Some of them are going to be authentic. Some of them are not going to be authentic. You have no idea to know which points are the correct ones. So in this example, the outliers are going to have small magnitude. So this is something that adversary can choose for you. This doesn't seem like a really good idea. So then you can say, well, let's remove points with large Mahalanobis distance, and the problem is the same problem. So the adversary chooses those points, and basically it's not going to work out. And you can look at other approaches. I don't know if you're familiar with Style-O'Donnell distance. This is another distance measure, and again, the adversary can choose it in a way that the noise drowns out the signal. And then you can look, well, let's look at all sort of estimation, an estimator, ellipsoidal appealing, and so forth. I'm not going to get into all those methods, but at least we haven't been able to make them work in this regime. So the point is that really those approaches work for d equals 5, d equals 7, and that's it. I mean, they're not going to scale up to more than that. Okay. And then there is the issue of tractability. So you want an algorithm which is tractable, so it should be polynomial in the dimension. And one approach is, which I mentioned before, the minimum volume ellipsoid. So in this approach, you take an ellipsoid that has a minimum volume and covers all the data, and you start shrinking it, and then you throw away points that do not add. You sort of look at the ellipsoid that contains, say, 90% of the data. And that seems like a very good idea in all dimensions. In high dimension, it's ill-posed because, well, any ellipsoid that you're going to take, if n equals m, so if the dimensionality equals the number of data, then every ellipsoid that covers all data has a volume of 0, because basically everything is flat completely. And then if you're going to say, let's try to still do something and remove a fraction of the points, you're going to get a combinatorial problem. And you can do something like a projection pursuit. That's also not going to work. So in projection pursuit, you're just going to look at the best projection in terms of variance, and then the second best projection, and so forth. That's not guaranteed to work in any way. Okay, so basically, we are not aware of approaches that do work in this regime. And what I'm going to do now, I'm going to present an approach that does work in this regime. And the idea is of the approach is it's really very simple. So the idea is that we are aware of the fact that we cannot throw all the outliers. So some of the evil points are just points we cannot identify, but we'll keep them if they don't harm our computation too much. So either if a point harms the PCA by much, then we're going to throw it away. If it doesn't harm it by much, then we don't care too much. So let me explain the main idea of the algorithm. So first we assume that D is known. So we assume that the dimensionality is known. That's a big assumption, but without that it will make our life difficult. So we get a candidate direction from standard PCA. So we do PCA on all of the data, no problems. Then we project the data to the low-dimensional space. We use what's known as a robust variance estimator. I'll explain what it is. It just estimates the variance on the low-dimensional space. And then we have, there are two things that can happen. Well, if the outliers are far from their origin, so if the outliers contribute a lot to the variance, we're going to throw them away. If they're close to their origin, so they don't contribute much to the variance, we're going to keep them and say, well, they don't harm us too much. So we do the projection, and then we do the removal of points which are strange. Okay, so points that looks to have a large variance. And what are the properties that we want to obtain? So we want the algorithm to be tractable, so let's have the same complexity as PCA, essentially. We want it to be robust to outliers, so we want some performance guarantees, which we'll provide. We want it to be asymptotically optimal, which means that if the number of outliers is little O of n, so if you have very few outliers, then you want to have perfect or near perfect recovery, and you want your algorithm to be kernelizable. So let's just, I'll remind you the setup. So we have TOS authentic samples in RM, and they're generated according to the model that is written here. So every sample is the signal A times, this is what we're trying to recover, A, times X plus noise. Noise is assumed to be univariate Gaussian. And we have outliers, and we observe everything together, and we want to sort of recover A. So let's explain what I mean by recover A. Here's the explanation. In one dimension, maybe this line here, this is the real matrix A, and this is what we recover. So the angle looks like something reasonable. So if the angle is small, then we're happy. We feel that our recovery is good. But in 2 dimensions, do you know how to compute the angles of 2-dimensional spaces? So there are ways to do that, but it's a little bit tricky. So what we considered is basically to look at how much variance is captured. So you want the variance to be captured by, as much variance as possible to be captured by your subspace. So here, when you do the projection on the line, you have a lot of variance captured. If you'll take another line, then you're going to have much less variance. So here, we have a lot of variance captured. Here, in this example, we have just a bit of variance captured. So instead of looking at angles, we'll look at what's known as express variance. So the express variance of a subspace that is spanned by principal components W1 to WD with respect to the true space is this expression here. And this expression basically it's a number between 0 and 1. If it's 1, then the subspace is completely spanned by the true principal components of spanned by W1 WD. And if it's 0, it means that it's orthogonal. In the case of 1 dimension, this is just writing the cosinus square of the angle. So this is sort of our measurement of success. We want this to be as close as possible to 1. So
just a second, please. Would the people on road sides please mute your mics if you haven't muted them already? Oh, sorry. That's good.
So this is just too excited. This is a very reasonable, I think, yardstick. So we just look at the express variance, and we want to find A that has express variance as close to 1 as possible. So I need to explain to you what's a robust variance estimator. So what's a robust variance estimator? You have a direction, say W, and then you order all your points from 1 to n. So you do the projection, and then you order them according to the magnitude, to the value from 1 to n. And then basically you take you throw away the smallest and the largest few, and you just compute the variance of the guys that are in the middle. So if somebody has contributes a lot to the variance, you just throw it away. And that's going to be that's called a robust variance estimator. And the reason is that the breakdown point of this very simple estimator is going to be not O of 1. It depends on the value of how many points you take. So it's decided to die. Okay. So let's just see the example that we have here. Here we have some samples. We projected them on a one-dimensional thing. We see that the outliers are in the middle. So their contribution to the variance is negligible, or it's small. So if the corrupted points contribute just a little bit to the variance, then we're going to discard authentic points, and then our estimator, our variance estimator, is going to be biased towards smaller values. But that's still not a big deal, because it's not going to be things are not going to go wrong by much. If on the other hand, the outliers are and they contribute a lot to the variance, then we're going to discard them. So basically we project, and then we think about something like from the 5th percentile to the 95th percentile, and compute the variance only of those projected points. So very simple idea. The breakdown point of this estimator is sort of same idea of like taking the percentiles, and it's going to depend on how many points you decide to discard. So is that idea clear? That's a sort of a classical idea in robust estimation. It's sort of works. So we have a pointer problem here. Okay, so here, just in picture, what happens to the robust variance estimator. So here we have outliers that are sort of closed, and what we're going to do is we're going to do the projection. So if what happens in the projection is that the outliers are somewhere up there, then it's not a big, then we're going to discard them and they're not going to harm us. If on the other end we do the projection and in the direction that we project, they're in the middle of things, then no big deal. I mean, it's not going to harm us in terms of variance estimator. So we're going to underestimate the variance, but not by much. So the algorithm is therefore as follows. You perform PCA on the empirical covariance in high dimension. So this is easy because you have an endpoints in n dimensions, but you find the d-dimensional space that best explains the variance. If the robust variance estimate on the PC direction is the highest, then you record it and you record the PCs, and you're happy. Then you randomly remove a point which is proportional to the variance along the principal component. So you compute the variance of every point, how much it contributes, and you randomly throw away a point. I'll explain why randomly later. Then you repeat until you have removed enough points. And enough will be explained there, and then basically you output the last principal components that you recorded. So the algorithm is very simple. I mean, all of it amounts to performing principal component, projecting on the space that you estimated, doing the robust variance estimate, throwing away a point or a few points randomly, proportion to the variance, and repeat. So the algorithm itself is kind of something you can code in 20 minutes in MATLAB. Questions?
I wonder, because you mentioned that initially the PCA can be corrupted completely. So,
right.
you start actually in the direction that the adversary.
That's right. So think about, like, suppose there is one point which is really out there in the moon. Not something that changes everything. So when you do the principal components, this point is going to, the direction, the principal components will include this point in their direction. So this point will have a very large magnitude. And then when you're going to randomly remove a point in proportion to its variance, with very high probability, you're going to throw this point away. Okay, so the first few steps, you're absolutely right. I mean, you expect to be mostly discarding adversary points in the first few steps. If of course you have many outliers, so if your data are essentially just outliers, then you're screwed. There's nothing I can do for you.
Question. Then is there any possibility that you throw out the true data?
Yeah, so there is a possibility to throw out true data, and we have to control this probability. So the results that we can get is going to be in terms of the fraction of outliers, because our algorithm will inevitably throw authentic points, and there's nothing we can do about it. So let's be a little bit more precise here, just to make sure that we're on the same page. So you perform PCA on the empirical covariance matrix. So you get the principal components. Then you compute the robust variance estimator that we showed before, and if your variance is large or larger than you've seen so far, you update your PCs. Then you randomly remove a point that's disproportional to the variance along the current PCs, and you repeat until enough points were removed. And then you output the last recorded principal components. So the algorithm itself is very simple. Every step from a computational perspective, all that you need to do is you need to do PCA, which is easy. You need to compute the robust variance estimator, which is easy, and you need to go over the samples and throw away one of them. So the algorithm is a polynomial, and it's random, but it works pretty well. So what can go wrong? So you can remove authentic points, and you will remove authentic points, but that, as I said, it's not a big deal. You may ultimately report something which is not the best because you threw away some points, and you can also have corrupt points that are going to remain in your data set. So, and they may contribute to the reported PCs eventually. So those three things can go wrong. But I mean, from a technical perspective, we can show that you can control those errors if you choose the parameters of the algorithm carefully enough. So let's just, I'll just show the guarantee. I'm not sure if I'm going to go into details into the proof. So the results that you're going to have are going to depend on the outliers, that's lambda, and the tails of the signal. So x, the signal, has some tails, and things are going to depend on that. Here, just to find this is so it's a complicated expression, but essentially it measures how concentrated the signal is. So this is sort of a measure of concentration of the signal. And in general, there is a theorem, or the main result that we have is that the express variance of the output, and I omit the probabilistic term here, so with high probability, the express variance is going to be lower bound by multiplication of two terms. The first term is the error that we have because we're using a biased estimator. So the robust variance estimator is a biased one. It's going to underestimate the variance. And the second term is due to random removal, so we may not remove all the outliers. And so here's our parameter that measures how many outliers we are going to remove. So what's interesting about this result, and again, I don't want to get into all the details, is that if the number of authentic sample, the number of outliers is little o of n, so basically, overwhelmingly the samples are authentic, then what's written here is 1. So your express variance is 1. And the other interesting point is that the breakdown is half. So if the adversary wants to change and to arbitrarily affect the eventual subspace that we choose, it needs to change half of the points. That means that the algorithm will perform well if you only change 10% of the points. But to arbitrarily change the subspace, he needs to change half of the points. Okay. So what's the proof idea? And the proof is a bit lengthy, but there are several key points. So one key point is the lessening of dimensionality. So high dimensions, instead of thinking about it as a bad thing, it's really a good thing. And the reason that it's a good thing is that, well, we know how to. This is really weird. So we know how to do load of large number and concentration inequality when you have many samples. But here we have many dimensions, and we can do the same thing, the same tricks, also when we have many dimensions. And that's exactly what we do here. So we use the number of dimensions to sort of get rid of the noise. So that's the first idea, which is kind of interesting. And really, the key point is that empirical covariance estimates are good even for high-dimensional regime. The second point is a random removal point. So here is we want to be in a win-win situation. So when we throw away a data point, well, either it's an outlier and then we're happy because we're getting less outlier, or that we throw away an authentic point, but then we're happy because the outliers look like authentic points. So we want to be in a situation where the random removal is if we throw an outlier, we're happy. If we don't throw an outlier, we're also happy because we have a good solution. And therefore, at some iteration, at early iteration, the algorithm is going to find a good solution, and eventually, we want to show that the robust variance estimate does not screw us too much. It's going to screw us a little bit. That's going to be the first term here, but it's not going to screw us by too much by underestimating the variance. Okay. So I'm not going to get into the details too much. I just want to show you one thing which is very useful here, and that's the theorem here, and this is really the essence of the first step of the proof, and that's something which I think it's worthwhile knowing. So if you have a general Lipschitz function and with respect to Euclidean norm, then you have a very general, very strong concentration inequality. So for every function, the probability that it's going to deviate much from its mean is upper bound by this term, and this is dimension free. So really, this is where dimensionality kicks in. So when we look at the covariance, that's going to be the object that we're going to consider, then the covariance of the low-dimensional projection is going to be very close to what it should be. And in order to do that, we look at the dimensionality, not the number of points. So you have a very high dimensionality, and you sum up things across high dimension, and then you can use those kind of results here. And as you see here, those are dimension-free results. So basically, that's going to save the day. So why is random removal a good thing? So here's a sort of a simple view, maybe simplistic view of things. Well, what can happen? Let's say that a good event is an event where the variance of the authentic points is upper bounds the variance of the corrupted points. And here is some factor that is 1/k is bigger than 1. So this is in terms of the variance. This is the variance of the authentic points. This is the variance of the corrupted point. And basically we say that the variance on the direction of the PC, we want it to be mostly due to the authentic samples. So if that's happened, then we're fine. I mean, the outliers did not hurt us too much. So in every step where we do the random removal, well, two things can happen. Either the step is not good, so basically some corrupted points contribute a lot to the variance, and then in that case we are going to eliminate points in probability that is proportional to the variance. So the probability that, I mean, this is some detail, but we're going to have one less outlier with probability kappa over 1 over kappa. So there's a small but bound away from 0 probability to get one outlier less. So what can happen? Either we get one outlier less, and then in the next step we're going to have one less outlier to worry about, or that we are going to have that we have a good event, meaning that most of the variance is due to the authentic points. So therefore, we are just getting either we're happy or we're getting rid of authentic points. And the output of the algorithm, basically, we will find at some iteration a good solution. So and then we also, I mean, the RVE, as I said, the robust variance estimator, we need to control for it, and that's something we need to worry about. There is one slight complication, and that's a good event. So we need to know that there is a good event with high probability, and that so then either, as I said, either the expected number of corrupted points is eventually it goes to 0, or that we have they're essentially indistinguishable from the authentic points, and we can do that with basically just looking at the number of points of authentic points that survive. Okay, and then eventually we need to control for the variance. I'll skip that. So one thing that you can ask is, well, in the second slide or so, I told you about kernelizing. So what happens with kernelizations? And well, as we know, we can do kernel PCA, and everything that I mentioned so far will still work out fine. So PCA, which is a source of high dimensionality, everything that would work out fine. You can still compute the PCA. You can compute the robust variance estimator, and basically I can give this talk again, but just talking about kernel PCA. So I guess not very surprising. Okay, so to conclude, so I mean, in this talk and this line of research is the first step to handling the case of where observation and dimension are essentially the same, and you have a lot of outliers. That's a setup that, at least in problems I've been working on, is quite important. And the key idea is that you project to a low-dimensional space. You have some robust statistics there. You verify it. If it looks right, you're happy. If it doesn't look right, you discard points that do not match what you think should be. So the noise models can be very general, can be sub-Gaussian, low concave, quite general. It works very well in simulations, and we get something which is pretty close to the curve that we want to. You can generalize it to other problems that have graphical structures. You have a probabilistic model, and you want to say, well, my data is generated by some generative probabilistic model and some outliers, and now I want to sort of figure out what's going on. So the outliers are going to either that they look the same or that they look very different, and you can do exactly the same trick for temporal, in this case, for dynamic Bayes nets. And you can extend it. We've been working on extending it to stochastic programming which is the very second slide with sample data, and do something which is low rank based approach. So this is sort of, as far as I know, this is a new regime to work on. And this regime is interesting because from a statistical perspective, the first point makes it very interesting to analyze, and the second point makes it hard. So the first point is solved by the blessing of dimensionality. The second point is solved really by having a high dimension, having this probabilistic rejection procedure, which is essential. I mean, and one before I conclude, you can ask, well, why do you need to throw things probabilistically? Can't you throw just, do a robust Variance estimator, just always throw away the highest guy? Then, well, the answer to that is twofold. Well, first, it will probably work, what you're suggesting. But if you want to prove things, I don't think it would work, because you really need to have this independence property that you use to assume that the number of authentic points decreases. But what's crucial in the proof is that you need to have a good event. So you need to either get rid of all the outliers or get rid of all the outliers that you can distinguish. And if you do it deterministically, then this proof-wise, it's not going to work. In the simulation, it works all the time.
Better?
The same. I mean, it's quite the same. Usually, it's very easy to detect such outliers until it becomes very hard. So usually, the way it works is that it's very easy to detect the first few, and then, like you're saying, well, nobody's going to distinguish, and I'm all set. So that was it. I think the next is more details about the proof. And if you want to, I didn't get into the details of the proof. I think it's an interesting result, but I wasn't sure that the crowd here would be pleased. And, I aim to please. All right, so thanks. Yeah.
When dimension is high and the number of observations is small, so observations are very expensive in a sense.
Right.
Have you considered that maybe not the whole observation is contaminated, but part of it? Or like one variable out of 1,000 is contaminated and the rest
Is not.
And then you wouldn't want to remove the whole observation, just save what you have. And
So the short answer is no. The long answer is yes, but it's hard. And the reason that it's hard is that you don't really know how to complete. So suppose that I do just a PCA, and I tell you, sample number 14, feature number 72, screw it somehow. What they're going to do, you need to somehow complete it. So unless you do some you have some self-reinforcing procedure, like bootstrapping, I don't know how to do it in the basic PCA. Mm-hmm. With the exception of bootstrapping, that has its own issue. So it's a really, I understand where you're coming from. It's obviously very important. I don't know how to handle it in any way better than bootstrapping.
okay.
If you have the low-dimensional model, you know to complete.
Of course. But then that would be bootstrapping. I'll be reinforcing my own belief.
Yeah.
I was trying to handle it as a missing data problem. Like once you identify the missing value, the contaminated value, you just remove it, forget about it, and then you have incomplete data and try to deal with incomplete.
Right, but even that seems very difficult.
Yeah, it is.
And it's a very important problem, obviously. So this is clearly something that is a worthy thing to tackle.
Question?
Yeah.
The number of outlier proportional to the true data is unknown, right?
Yes.
So how many outlier you would like to take out?
Okay. So in principle, you can take out all the points. So you take them one by one. From if you have n points, you throw everything out eventually. But you guarantee that along the way, you will have a good solution, and you have a certificate to which solution is good. That's a solution with a maximal variance. Okay, so in principle, you don't really need to know this fraction. If you know, then you can stop earlier, because at some point you're not going to get anything by just throwing away authentic points and redoing PCA.
Okay, so that means choose the best from the history.
That's right. You choose the best from the history.